Hello, so in this tutorial we're going to see how to use Rosette for program synthesis. So a short reminder of what program synthesis is the general problem of finding a program that meets a correctness specification. And often this correctness specification can be expressed as a set of input-output examples or as a logical formula. And finding a program means that we have defined a search space for that program. So it defines what kind of programs we can look for. In this tutorial, we're going to see how to use a syntax-guided synthesis solver. And the specificity here is in the specification of the search space for the program. The search space is given a syntactic description that will define all the programs in our search space. And how is this syntactic description built? We have a sketch plus an expression grammar. A sketch is a program with holes. So for example, this small bracket function is incomplete. We define f, function of x, y, z, where if x is less than something, where this something is undefined and we call this a hole, then we return y or z. And this unknown is a hole to be filled with an expression, and this is where this expression grammar comes in. We can define this hole to be filled with either x or y or z, or 0 or 1, or an expression that is an expression of the same kind plus an expression of the same kind. So for example, x plus 0 is an expression that can fill this hole. And this is the syntax-guided synthesis solver, so Rosette in our case, that will fill the holes for us given a specification for f. So for example, if we want f to be the function that returns y when x is negative, then the hole will be filled with 0. So how do we specify a problem in Rosette? So how does a file for the program synthesis problem look like? First, you have to start your file with the language declaration. So in Racket, it would be #lang Racket, but for Rosette, it's #lang Rosette. Then you can give all the definition of your specification and constraints and helper function that constitute your problem. The main part here is the definition of the synthesize construct. So the solution will be returned by the synthesize construct, which takes as argument with keywords for all list, where list is the list of variables that are universally quantified in the problem. Then an optional assume constraint, where the constraint has been defined previously. So you can add constraints on the variables that are in the for all argument. And then the guarantee part. This is where you put the specification. So in this problem, for example, we'll have a solution such that for all the variable in the for all, the list of for all, assuming that these variables satisfy the constraint, we have the guarantee that the function f that will be synthesized satisfies spec fx, where its some specification for f is satisfied. And we'll see an example where we're trying to find the factorization of a polynomial. And you can find the same example in section 2.3.3 of the Rosette guide. We start by the language declaration, so #lang Rosette, and then we import a library for defining holes in the sketches. Let's assume that we have an original function that represents a polynomial, so we define poly of x, which is the sum of x to the power of 4, 6 times x to the power of 3, 11 times x squared, and 6 times x. What we want to synthesize is the factored form of the polynomial. So we define factored of x as the product of x plus 1 and then x plus something. And this double question mark is a hole for Rosette, and it will be filled by some integer. And this integer will be chosen by the solver. If we want the synthesized polynomial to be equivalent to the original polynomial, we need exactly 4 of these factors. Now that we have written the sketch, we can start expressing the synthesis problem. More specifically, the constraints of the synthesis problem. We want for all x integer, poly of x equal to factored of x. So we can define the constraint same p f x, and this constraint asserts that p of x is equal to f of x. Now let's use Rosette to solve our synthesis problem. So we define the solution to be the result of synthesize for all x, the guarantee same poly factored x. And remark that in the same constraint we needed the assert, and Rosette guarantees that the solution synthesized will not violate any assertion. So in this case, the solution synthesized will not violate the assertion that p of x is equal to f of x. One last thing we need to do is define this x that we're using in the constraint. So x is not just a normal variable in bracket. It's a symbolic variable that we're quantifying over. So the way to define this variable is to use define symbolic, and then we give the name of the variable, and then we give the type of the variable, an integer. Finally, we want to print the solution. So if the solution is sat, then we call the print for functions on the solution, and this will print the solution. Otherwise, we just print unsat. Now let's call the solver on this synthesis problem. So we do this by calling bracket on the file that we just wrote. So in this case, it's called tutintro.rkt. And when we call this, we get an answer, and this means that the problem is satisfiable. So we have this defined factor of x with the solution. And if we put the solution just next to the sketch that we wrote in the file, you can see that each of the holes has been filled with an integer. So the first hole has been filled with 3 and so on. In this short demo, we've seen how to use the synthesize construct and also how to declare symbolic constants, which are the constants you can use in the for all part of the synthesize. If you want to declare integer constants, you use define symbolic, then the list of variables you want to create, and then integer, which is the keyword for the type of integers. The same thing applies for Boolean constant. Define symbolic, then the list of variables you want to create, and then the Boolean keyword. We've also seen how to use a basic type for holes, the integer holes, which is this double question mark enclosed in brackets. And you can see the relevant sections of the Rosette guide for more information. In a second demo, we will see how to define grammars for the expressions. The most basic is the double question mark in parentheses that we saw in the previous demo. Another possible construct is the choose operation, which allows us to define a choice of different possible expressions. And then there are two defined syntax macros. The first syntax expresses a macro for defining simple definition of expressions, and then the second syntax is a macro for recursive definition of expressions. We will use both syntaxes in the next example, and it will help you understand how to use them and when to use them. Let's start by writing the skeleton of our file. So we always start the file by #lang Rosette, and then we define the solution to be the result of synthesize for something in the list, and we guarantee some specification that we'll write later. The problem we want to solve in this demo is to find a function to join two partial maximum prefix sums. The maximum prefix sum of a list of 4 elements is the maximum of 0, x1 plus x2, x1 plus x2 plus x3, and then x1 plus x2 plus x3 plus x4. We can do the same thing for a list of 8 elements. So if we write this mps8 function of x1 to x8, and we copy the definition of the previous function, and we add all the other prefix sum, we just need to take the max. Let us specify the synthesis problem. First, we need 8 symbolic integers x1 to x8. In the synthesis problem, for all x1, x2 to x8, we want a join function such that the result of joining the maximum prefix sum of x1 to x4 and the maximum prefix sum from x5 to x8 is equal to the whole maximum prefix sum, that is the maximum prefix sum of x1 to x8. And then if this solution is satisfiable, then we print the solution, otherwise we print unsight. Now let's write the join function, which should be a function of MPS1, the maximum prefix sum of the first part, and MPS2, the maximum prefix sum of the second part. And we don't know yet how to write these functions. We just know it should be some function of MPS1 and MPS2. Let's start by using the choose function to write a first version of a sketch of the join function. So choose x1, x2 means the solver can choose between x1 or x2 for the implementation. Here we write an expression where the operator or the function is either max or plus, and then for the arguments we can choose between MPS1 or MPS2. And we have to import the Rosette lib syntax library to use this choose construct, the same way we needed this library for the integer whole, which is a double question mark. Let us call the solver and see if we can find a solution. As you can see, the solver returns unset, which means there is no program that satisfies the specification. Before modifying the sketch, let us remark that the join could need more information. So we are going to add two arguments, the sum of the two parts. We will also modify the sketch to get a more complex expression. We add the new sum in the choices of variables inside the expressions, and then we copy this expression inside an expression where we give a choice of operator. Now a solution has been found by the solver, and you can check that it is correct. Now we have a sketch and expression grammar that contains a solution. We are only going to rewrite this in a more concise way. First, let us write a macro to replace the operator choice, which is the same everywhere in the expression. We do this by using define syntax with an identifier as its first argument, and then an S expression, and in each sub-expression, a pair of pattern and its expression. In this case, it's just one pattern and expression pair, where the pattern is just the operators, and then the expression is choose max, plus, and minus, for example. Finally, we replace the choices in the sketch by this new macro, and do not forget to add the parentheses around the macro calls. Now let's check that the solver still finds a solution for our synthesis problem. And as you can see, it is the case. We can also replace the sub-expressions by a macro. Let us write a binx macro, and we want the result to be exactly this binary expression, where we have the choice of a binary expression and the choices of variables as the operands of the binary expression. So this time the pattern captures also the arguments sum1, MPS1, sum2, and MPS2. Now we can replace the sub-expressions in the sketch by just writing binx all the arguments. And finally, let's see what solution the solver returns. Let us try to write an even more concise sketch. We can define a recursive syntax of expressions by using the construct define syntax, with the first S expression being the identifier, then a list of arguments, and finally an integer k that is the height of the expression. Remark that in bracket x with triple dots means a list of arguments of undefined length, but at least one. In this definition, we have a base case for k equals 0 that corresponds to the leaves of the expressions. In our case, we put a choice of some x with the triple dots to mirror the arguments, or 0 or 1. And then there is the recursive case. In the recursive case, we construct an expression with a choice of a binary operator using the macro defined previously, and then recursive calls to the same expression definition, but with a height parameter decreased by 1. Now we replace the whole sketch by this macro with the arguments sum1, MPS1, sum2, MPS2, and the last argument is the maximum height of the expression, which in this case is 2. Now let's call the solver on this new sketch, and we see that it finds a solution, which is different from the previous solutions found, in that now it has a 0 in it. So if you try it yourselves, you might find different solutions. There's many solutions for a given problem, but in each of the cases presented, you should find a solution. In this short tutorial, you learn how to use Rosette to synthesize programs. You express the specification using assertions, that is, the function is correct if and only if it does not violate any assertion in the specification that you put in the synthesize construct. In the second demo of this tutorial, we focused on writing the sketch and defining the expressions that the solver can use.